Okay, assalamualaikum and good morning, everyone. So welcome back. Hope you had a nice weekend. So again, please warn me if suddenly I'm get no disconnected or anything like that. Right. Today today we're going to continue our lectures. Essentially, lecture three. Previously, we had done things. So today we are going to look at entropy in much more detail. Uh, by the way, I have not finished typing the notes. At some point, I will switch from the typewritten notes to scribbling on the whiteboard. So let's recall about we define entropy previously by taking the case of a reversible process. Maybe I should go back to lecture 3 a bit. Sorry, the computer is slowing down. So let's recall lecture 3, what we did there. So we define entropy using some integrating factor previously. Okay, so we had that, and then we define the absolute, we define the Carnot engine and the cycle. And then I think the final thing that we did was, defining the absolute temperature. But let me go to this picture previously. Must be somewhere. So let me get back to this picture. So here is essentially a Carnot cycle. So represented by what you call, can you see the cursor? Okay, good. So here we have the isotherm, and then over here you have your adiabatic process. So in adiabatic process, you don't have heat taken in by the system. So here is another isotherm, and then you have your adiabatic compression. So we had those previously, so we're going to recall those again in this lecture. So here, if you look at this particular context, here Q1 is essentially the heat taken by the system when it goes through this process of isotherm, and then Q2 is the heat released by the system as it goes under isothermic compression. Okay, so today we're going to look at these processes again. We need to set a kind of convention over here so that Q2 was written without a negative sign before. It's like in the case of Q1, excuse me, okay, there's a delay a bit. Q1 over here, then essentially, oops, where has my lecture 3 gone? Okay. Q1, and then this follows this particular, I think it was here, sorry, let me go down. Okay, so you have this differentials, okay, which is not exact given by the work done there. And then we will use the fact that we can use the integrating factor previously. So again here, just to recall what we did. This is the case, I did guess. The one, okay, the one here. Sorry. So you had this factor here. So over here we have not your Q2 over here is without the negative sign, but here your Q2 is negative. Okay, because Q2 is actually heat release out, but it's written in such a way so that it becomes it has this nice symmetric formula. But we now want to introduce back the negative sign so that it denotes. So now, for example, Q2 is positive, but with the negative sign, this whole thing is now negative. Okay, so it's just replacing the previous equation so that you get this notion of heat being released over here. Okay, so so when you do that, so we can rearrange this. For example, Q2, you take T2 on the other side and Q1 on the other side, and then you rearrange the formula or rearrange the equation. Then you get this equation of heat divided by the temperature under this particular reversible process is going to give you equal to 0. Okay. So so that is what so this is coming from the previous picture. Let me see if I can use my tablet here. So this comes from your previous. Oops. Okay. So now this is okay. This is negative Q2 to denote that this is being released, and Q1. Okay. So under the reversible process, this is actually equals to 0. Okay. So one can now not being limited by a Carnot cycle. So this is a Carnot cycle previously, but one can just think of a general reversible cycle. So it's an arbitrary reversible cycle. So here is the circle over here is an arbitrary reversible cycle. But you can think of this arbitrary reversible cycle being made up of a smaller Carnot cycles. So one can draw all these families of line for adiabatic curves. Okay, the one above here is essentially an adiabatic curve. Okay. So over here on the picture from the book, so here's the families of adiabatic curve. You can actually see it's been drawn. And there's also the isothermal curve, which is given for this part in the Carnot cycle. So it's been joined between one, let's see, here's process 1, adiabatic process 1, and here's adiabatic process 2, for example. So this is actually been joined by this isothermal. So here is the isothermal. Okay. So you can think of this as being, there are families of those, and then you have these adiabatic processes being joined up by what you call lines. Okay. So here this so-called the tiny Carnot cycles seems jagged. Is because we use a finite number of selected points. Okay, so if one can imagine that this finite number becomes the selected points become infinitesimal, so this one becomes infinite really. So when it does that, it will smooth out this jagged thing, and then becomes the arbitrary reversible cycle. Okay. And the other thing that we need to understand is, because this is like a sum of Carnot cycles, okay, but many of them. So you can see that, for example, in this process, so this is Carnot cycle here. This process, you can see that it overlaps with the second Carnot cycle underneath, okay? And you can see that there's a what you call common adiabatic process here. So the common adiabatic line will will have opposite direction. It goes this way for the top one, and it goes the other way for the bottom one. So in other words, the work done made by this process will be what you call vanishing, okay? Because when you sum it, it becomes two different reverse, two different direction in the opposite sense. So those kind of work will cancel off, and then effectively what you have is essentially just your processes given by this general reversible cycle. Okay. And remember that the adiabatic processes doesn't take up heat, so the heat is taken up during the isothermal process, so during this connection here. Okay. And then in those tiny cycles, so heat is taken in a way that is infinitesimal, okay, so it's taken in a rather small amounts, okay. So one can actually write the following now in each of this tiny cycle. Okay, remember that we had earlier Q1 over Q1 over T1 plus Q2 over T2 equals 0. Previously, this is for a finite case. So for the infinitesimal case, we have the following equation. Okay. So you can sum that up. Okay, as I mentioned, the case for the adiabatic, the common adiabatic processes, they will cancel off each other, and then you can sum it up. Then since each cycle is actually behaving in this manner, then for summing up all the what you call tiny cycles will also give you 0. So in the limit, so here is essentially smoothing out the thing. So in the limit, it's just like an integral over a cycle. Okay, so this is over a cycle of dq over t, and that will be equal to 0. Okay, provided remember that this is only for reversible cycles. So one of the things that we know about this kind of an integral over cycle equals 0, that means essentially this particular quantity is going to be conserved. Okay. So let's look at a different thing so that we can understand this a bit better. Okay. So here's a cycle given up by two different paths from the point A to B and then B back to A. So you can compose them to this different path. So you have path 1 over here, and then the integral goes from A to B, and then path 2 is going from B to A, and this essentially is a cycle, so this will be equal to 0. Okay, but in a way that, okay, what I'll do is bring one, let's say the path 2 onto the other side, and that gives you a negative. So the negative part, we can actually remove the negativity by changing the limits, and essentially what we have is this thing. Okay, so in other words, here we have two different paths, path 1, path 2, but connecting the same endpoints, and they are equivalent. So in other words, the integral that we had is actually independent of path, which is more or less already sorry, there's a lag here, which is already what you call implied in this particular integral over a cycle there, okay, being 0, okay, and then essentially it also is independent of path, and also the quantity that is represented over here, whatever this quantity is, which are equal in these two cases, okay, they will depend only on that endpoints. So this is precisely the thing that we have mentioned before. Then these endpoints will be your state variables, and the integral itself is going to be a function of the states. Okay. And we have seen this actually before. So in other words, we define this to be what is known as the entropy. Okay. And usually what happens over here is that the lower limit, okay, so the lower limit is going to be some reference point. Now, depending on the system, these are taken usually at the lowest temperature of the system. Okay. Now, ideally, the lowest temperature would be absolute 0, but unfortunately, in experiments, you don't actually do that. It's not practically possible to cool down system to absolute 0. So you look at the lowest temperature instead. Okay. So so as I said, we can do this infinitesimally. So we can actually see the infinitesimal change of entropy. Given by this quantity of heat and at the temperature T. Now let us recall a bit. So now we have this definition. Okay, let's recall a bit our first law using the internal energy, which is dq plus, sorry, here it's going to be minus here. Oops. du equals to dq minus p dv. Okay. So now what one can do is to rearrange this equation so that you get T ds equals to d bar q, and replace it over here, and then essentially that gives you that. Okay. So in other words, dq we are replacing with that. Okay. So another thing that we had earlier was to think of your heat capacities. Let me see if I can get to that formula before. Heat capacities, where do we learn that? Oh, that must be in the first lecture. Okay, never mind. So the heat capacities are given by something like the amount of heat at the temperature T, right? Let me just open the lecture 1 instead so that you can see. My computer is not behaving properly today. Oops, what did I do? Come on. No. Okay, never mind. So you can look it up, okay, in your lecture notes, and one can now rewrite your heat capacities at constant volume, constant pressure, as the temperature multiplied by the differential of the entropy with respect to temperature. Okay? And this will actually help us to define how entropy is actually measured. Okay, so which is the next topic. So one has this, for example, the entropy change. Okay, given that now you consider heat, the processes that you are taking essentially all reversible processes, and so you take a process reversible, so then this is going to be independent of path. So I consider at one initial configuration or initial state to another final state. Okay, so in this is well defined, and then you remember at constant pressure you have this condition, so it's dq d over t essentially previously, and then you have Cp there, so you replace that over here, and essentially that will give you the necessary formula to be able to measure entropy. Okay, you look at how this heat capacities as a function of T integrated from the initial configuration to the final configuration. Okay, and in the case that we had for the work being only expansion and contraction of the system, and there's no other work, then you can actually rewrite this as follows. Okay, it's just the integration of that. Okay. Here we assume the assumption here, if this is constant. Why is it not? Okay. If it's a function itself, then one needs to do the proper integral for that function of t. Okay. For our cases, the simple case, then we can get that. Okay. The only part that still is unsettled is this one. Okay, so here there's an arbitrariness that we need to check on later on. Now, this formula seems to suggest that your entropy is a continuous function of temperature, but this is not necessarily so, because what happens, the system can undergo changes of phase. An example given in the book essentially is that liquid goes to under boiling condition, liquid vaporize, and in the case of superconductors, remember that superconductors is when you cool down the material to low temperatures, but before that, it's actually if it's a metal, then it will be a normal metal, or if it's in the case of high TC superconductor, for example, this will be an insulator, for example. Okay, so and in those cases, then you find your entropy does not need to change smoothly or continuously. Okay, so what happens in those particular cases? Let's consider the easy case of a system in liquid and solid phases in equilibrium. So you have both the solid state as well as the liquid state. In say ice water, for example. Okay, and these are in equilibrium at a particular temperature called phase transition temperature. So in the case of the ice water, then it will be 273 Kelvin. Okay, and at that temperature, one can actually define again another change in entropy due to this phase change, and it's given by this. Okay, it's just the heat taken in, for example, for the ice to melt, heat taken in by the system, but it doesn't quite raise the temperature, and this is normally written as a change in enthalpy, which have defined earlier, and in high school, I think it was called latent heat. Okay? So we need to introduce those ideas inclusive with the functions that we might see from the integral over here. Okay. So generally, what's going to happen? So I need to go to the whiteboard. Finishes there. So generally, okay. Before that, if this delta H is greater than 0, then the process is called endothermic. That means the system absorbs heat. Sorry, and if your delta H is negative, then the process is called exothermic. And actually, what happens there? The system releases heat. Okay. Okay. So now I have to go to the whiteboard. Let's see. So in other words, okay. So I have to introduce some other things. Okay. Let me go to the whiteboard. What's happening here? Can I write something? Sorry for this. Are you seeing the blue screen at the moment? Okay. Let my PC, my laptop is not that powerful, so probably has too much open windows, I suppose. Okay, it's coming. Okay, whiteboard. Let me clear that thing out. I think I better close my one or the my. What's that? Okay, let me. Sorry for this. Okay, let's hope now it can work. Let me close the PDF as well. Sorry guys, my laptop is not functioning well today. Okay, I hope that has enough memory. So let me go here. This seems to be responding. Great. So let me go here. Oh no, man. Let me just continue if I can write things down. So ignore this. One could actually measure the idea of entropy of phase change, but normally what is done is you do this in experiments. So there is, okay, now it's coming back. Oh, yeah. Okay. It's taking too much my. Right, okay. So there is what is known as Trout. Let me look at this. Troughton's rule. So this is how you actually. Troughton's rule is basically looking at entropy of vaporization. And for various liquids, this is known to be around this value 85 to 88 joule per Kelvin per mole. Okay, and these are liquids with simple intermolecular interactions. And you can look it up, this Troughton's rule, from Wikipedia, for example, to see this. Intermolecular interactions. For much more complicated cases, like water is one of them. Okay, water is an exception to this rule. Troughton's rule, and the entropy of vaporization for water in this case is given. In fact, this is given in the book, but not much details are given. One can actually look up Troughton's rule elsewhere. This is 30 kilojoules. So that is 30 times 10 to the power 3 kilojoules. Let me see, I can read my own handwriting. Per mole. At 273 cube. Oh, vaporization. Sorry, vaporization. That would be 373. Let me check that. 3. The ones given here is can't seem to find it. Yeah, this will be the vaporization. So this is okay. So you can calculate, but still not the over here is kilojoules compared to joules over here. So why this is this happening? Because water is made up of hydrogen bonds, and these hydrogen bonds have complicated molecular interactions. So that's why you have this higher entropy of vaporization. So in other words, your entropy of vaporization can be determined through the idea of latent heat. Okay. And then essentially that tells us about entropy. Okay. Let me go down. Oh, that's going the other way. Okay. Are you seeing this handwriting thing? Okay. So generally one needs to look at all this, and let's suppose you consider the case of there's a let's say the change of phase over here only your melting and vaporization. Okay. Oops, we're doing it's messing my things. Okay, I want to go up. Sorry, not that. Okay. So if that is the only change of phase allowed, then essentially you can calculate your entropy in this way. So there will be a entropy defined at the reference point. As usual, this would actually be the lowest temperature there. And then for the first case is the melting thing. This will be so-called the fusion temperature. Fusion. And then CPT, ET over T. So this is the same formula that we have seen earlier. But now we need to include the latent heat thing. So this over here, fusion, latent heat of fusion over here, divided by temperature at the fusion temperature there. And then you go up again, so it goes from the T fusion, say until T boil, CPT, ET or T, and then add another latent heat of vaporization there, so that delta H, boil, T, boil, and then from T boil to T, the final temperature, again another integral there. So one has to include all this possibility into the formula that we had earlier. The one that's going to be problematic is this one, because this follows certain convention, and that convention is actually outlined by Nernst. I do not know how precisely to pronounce his name, but Nernst. What does it say is that, let me see. I can't see my notes. Sorry about this. I thought I had it. Oh yeah, okay. So essentially, over here, the entropy change as temperature goes to absolute zero, then the entropy change will also goes to zero. Okay. So this essentially lays the equivalent to this idea of the third law of thermodynamics. Okay. So we had this arbitrariness that we need to somehow use this law to actually define this. Okay. Normally what happens, one can also do extrapolation for the formula. So you can also try to do that to complete this formula to define what is this reference temperature. I think I'm going to skip some of the examples given in the book. The example given in the book is the case of there's a phase transition from a monoclinic sulfur to orthorhombic sulfur. So you can look it up in that book. So I'm going to skip that since I'm scribbling things on the whiteboard. Go to the other thing. So hopefully I'll finish off this thing. So we want to define what we call, so in other words, once we define this entropy, so we need to define entropy defined via measurable means. So given that happens, then we can define other kind of free energies after this. Enthalpy is not one of these free energies. So we need to define others. So the first one is, let's recall our first law. Which is written as du equals to T ds, previously it was q dq here, T ds minus E dv. Okay. Now I can now define as follows. So du, I can take this as dTs, and then there you can get your TDS, the one on top, but I have also SDT, so I need to take that away. Okay. And I can bring this to the other side, and then this will give me u minus ds equals to minus s dt minus p dv. So this is now an exact differential. We find this to be what we call the Helmholtz free energy. I hope you can read my handwriting there. This is given the notation F, which is defined as u minus ds. Okay, so this one is essentially df, written in terms of the differential dt and dv. So in other words, since I have that equals that, so then essentially I can think of your F, which is your Helmholtz free energy, to be a function. Here is the differential T and here is differential V. So I can think of your F as a function of T and V. Okay. So if I were to rewrite this as a differential over here, so this will give me what? Since this is a function of t and v, this would be df dt constant v dt plus df dv, right? But remember, from there we had df equals minus s dt minus p dv. So you can now see that I can identify this minus s with partial f partial t and minus p with partial. So here, oops, we have the following. We have s equals to minus partial f partial t constant v, and then p to be minus partial f partial v at constant t. Now if f is a analytic function of t and v, one would also require certain conditions. Why is it not going up? One should also require so analyticity of f requires the following: that partial v partial f partial t, sorry for my horrible handwriting, partial t is equals to partial t partial f partial v. And this is this has before, this is v, this is t. Okay, so we need that as your second order derivative is going to be interchangeable. Okay, and that tells us what? That implies, since we have already defined s and p through this derivative of this state function Helmholtz free energy, then what we have is this one translate to the s dv at constant t equals to partial p partial t at constant v. So this is known as Maxwell relations, and there are four of them. Okay, so this is only one of them. And the transformation, remember I did mention some time ago when we introduced enthalpy, going down. Sorry, this is a bit slow. Sorry about this. Come on, hurry up. Oh dear. So we use this kind of transformation. Okay. So if you we will go back to this afterwards. I don't think we have time for today. And I've forgotten that on Thursday we have a public holiday. By the way, happy Deepavali to students who are celebrating Deepavali. Before I forget, so here what we did was to change the differential that the relation has from ds dv. So this kind of changing from one dependence over here to another dependence over here is what we call the Legendre transform. And there are many such transformations. So over here we are changing from to do this changing of transformation between the dependent variables, sorry, the independent variables of entropy and volume here to temperature with volume. Okay, it's called Legendre transform, and you change the state function to from internal energy to what we call the Helmholtz free energy. There will be the other energies that we have gone through. We have the enthalpy, and then another one that we should define is the Gibbs free energy. But I suppose that is how much I can say for today, because otherwise I will be going over time. So there are two, the enthalpy thing, you can go back to the previous notes. I think we have defined those. So the only thing that's left is to define Gibbs free energy. So this next lecture, Gibbs free energy, enthalpy is already defined, and of course we have already seen internal energy. Okay, and each of these has their own Maxwell relation. So there will be four Maxwell relation, which of course is no, you can't remember all of them, but no, you can always try to derive this from this so-called Legendre transformation. Okay. So we'll do that hopefully in the next lecture. So let me go back to the screen. I hope you're all still there. The computer seems to... Okay, I will now take your attendance. And that's all for today. Thank you, everyone. Still waiting for the attendance list to be downloaded. It's not happening. Okay. So we'll end the lecture now.
Thank you.
Happy Deepavali.